All right, today we're going to talk about these 5 topics: machine, product, inspection, process control, and predictive maintenance. In the area of machine design, things like machining stations, bonding fixtures, runoffs, buy-offs. Before we take delivery of some new process, we send our thermographers out, have them look at all electricals, have them run the machine to see if it's reaching the target temperatures that it's supposed to. So it's a very cost-effective way to make sure that that machine is running and doing what it's supposed to. If there's something wrong with it, guess who gets to repair it? Not GM, but the supplier we're buying it from. I've been on many of these, and it's really cost-effective for a company to send out a crew with infrared to look at these new tools. Different cooling techniques. We put to rest a lot of arguments across the corporation on how to cool something in machining applications. What areas that haven't been cooled, we get distortion, so we can see that. We can redirect cooling techniques and really increase our throughput and our quality. Tooling studies, several of those under our belt, and what are good vendors, what are bad vendors on our tooling. We had when Delphi was part of GM, we had a big effort in the area of induction coil design. You can get 3 times faster coil designs by using infrared, watching that part heat up. We can also create a library of what coils can heat up what parts and what they look like under different times and power. And you can speed up your coil design process by a factor of 3 using infrared. And again, in the area of die casting, just a wonderful application list of what we can do with infrared. This is a Corvette hood. I'm going to talk a little bit about bonding fixtures and what we can do here. I was called out to a supplier down in Toledo, and they had 180 zones of heating on this hood to make sure that when the 2 parts came together, that it was cured properly. This is the bead path, I think about 150 inches of adhesive, and then the 2 parts were brought together and put into a mold for curing. This is the bottom part of the mold. It only had maybe 9 areas, maybe 12 areas, but the top half of the clamshell was the one with the almost 200 different heating zones. This is what the part looks like on exiting. SMC is a wonderful material. It holds its thermal gradients very nicely. What we're looking for is symmetry. If we look at it, popping out of the mold, we got 173 degrees here and 144. It's almost 30 degrees different. I don't know if you ever bake cookies at home, and when you got a cooking sheet you're heating up, you'll hear it go twang in the oven. That thing will take a bend because it's not heating up properly, or there's nowhere for some of the metal to go. Same thing with this material. If it's not heated up symmetry-wise, and you go to bond it, it's going to come out crooked. And then you got to take that crooked hood and put it on a perfect body, and it's supposed to fit. Flush and fit are supposed to be perfect. And then you have folks in that poor assembly plant that are tweaking those hinges, trying to make it fit right. Now the trick is back in the bonding process. You want to get this thing symmetry in action here. So we've got 172, 161, not bad, but look in the middle, 198. So we would tweak this area down, we would bring this area up. This was a hinge area that we needed some extra heat in, so those 2 areas needed to be brought up. So once we finished that out, we had a beautifully symmetry, balanced out hood. And before I could leave the company, I had to do a Ford part because they wouldn't let me leave. They saw how wonderful this technology was, so I helped them out to balance out a Ford product, and Ford owes me, by the way. So you folks from Ford back in the day. All right, next. Axles. GM makes some of the world's best axles. We sell them all over the world. Mercedes, BMW buys axles, or they used to. I don't see why they wouldn't still be buying axles from us. And in the heat treat operations, you want to be pretty careful on what's going on along the length of that. And on the end here, you can't have too brittle. It'll fracture in use. You want a nice tough end on it. So this is one of our first applications that we put in line scanning. This was back in the day. We had a Factory of the Future. The goal Roger Smith had back then was to have nobody in the plant, only machines, robots, and processes running that plant. In the area of injection or die casting, pardon me, this is the brain of a transmission. This tells your transmission when to shift gears as you accelerate down to your on-ramps onto the expressway. So it's pretty critical to get the thermal gradients across here. You want a nice flat part. There's some really deep weld areas that you have to worry about soldering. And understanding what's going on in the die casting process is critical. Some of the things you have to worry about are the die lubricant, and when those dies open up, this is the ejector side of the die, and you want to be able to spray things to cool down over temperature areas. Water lines through the die itself are critical. Biologicals can grow in those water lines, pinch off a water flow, and then you start having problems. How do you find it? Infrared imaging will help you. You'll see a hot spot. You look at your water line diagrams. You might look at the flow rate in that area. If it's not doing what it's supposed to be doing, 5 gallons a minute, 6 gallons a minute, you've got biologicals or something's plugging that water line. You can see that with infrared. Here's an area that's getting hot. This was that deep area. Extra die lube would take these temperatures down and reduce the chance of soldering. That'll shut your process right down. Once that machine stops and the folks have to pry off a part off of something that was soldered, then the whole die itself starts cooling. If you go to bring that back up to speed, you're going to be making scrap again until that die gets back up to temperature. So die casting is one of those operations. Once you get up to temperature, you never want to shut it down. Don't take breaks, bring other people in, keep that die cast going. When you look at the theory and look at our data, we go through several plateaus bringing that machine up to temperature. It takes sometimes hours for that to reach full running temperature. You don't want to tweak it unless you see data like this, and you don't want to shut it down for lunch, breaks, or on a weekend, unless you make production and you can go to another die itself, bring it up on Monday morning. So pretty critical application for infrared.